So today we're going to talk about artificial neural networks, the wondrous invention by Geoffrey Hinton that pretty much changed the world. I'm sure a lot of you who are into artificial neural networks, you understand how the basic structure is. You've got your input layer, which is connected to the hidden layer, which is finally connected to the output layer. So these are the connections between the input and the hidden layer. I'm not going to draw all of the lines because I believe these many lines basically gets the idea across that the nodes of the input layer are connected to the nodes of the hidden layer. Each of these input nodes, let's call this layer X, where X is a single vector consisting of the numbers that represent the input feature set. X is multiplied with the weight matrix W, and W is the weight matrix that represents the connections between the input layer and the hidden layer, and then it's added with a bias. So the input layer is multiplied by a weight matrix, let's call it W1, and then added with a bias matrix or a bias vector called B1. This forms the input of the hidden layer, which we shall call Y, is then passed through a function that we call an activation function to form what I shall call Y dash. The reason for activation function is two things. One is to introduce nonlinearity into the equation. Otherwise, without an activation function, a neural network is basically just a single linear function, which is not how the brain works, which is what the neural networks are inspired from. And secondly, because it's inspired from the brain, the activation function tries to emulate the fact that the brain's neural networks, they're slightly different from the neural network that we describe here, but they can only exhibit a maximum and a minimum of so many numbers. The Y dash, in turn, is then multiplied with another weight matrix and added with another bias to form the output layer. As an equation, this is represented as Y multiplied by another weight matrix, the weight matrix that exists between the hidden layer and the output layer, W2, and then is added with a bias B2 in order to form the input of the output layer, which we shall call Z. Z is then again passed through an activation function in order to form Y cap or Y hat. Some people like calling it Y hat, some people call it Y cap. Y hat is the output of this whole neural network and what we call the feed forward process of the inputs being fed into the neural network, which then passes on into the hidden layer, activated, and then passed on into the output layer and then activated again. Y cap or Y hat in this process will be the resultant probability of what class the input might belong to. That's a simple way of describing a neural network. What is more interesting is the way it's learned. The neural network learns what class the inputs is supposed to belong to. So this process of feeding in input in order to get Y hat is called the feed forward part. The learning is based on something called an error function. Simply described, an error function is how wrong are the predictions of the neural networks. It's a way of measuring the error between the predicted output and the actual outputs. We shall take an error function of sum of squared errors, which is a very standard error function or a very traditional error function when you're starting to learn neural networks, which will be denoted by the letter E. In other words, based on how wrong the neural network is, the neural network's weights and biases are adjusted in order to make sure that when this neural network is shown the input vector again, the next time its predictions will be closer to what the actual class labels are supposed to be. And we shall backpropagate the changes that need to happen in the weights in order for the neural network to predict the next time correctly. And backpropagation is a very interesting process. It basically says the weights and the biases need to readjust themselves based on their contribution towards the error of prediction. Mathematically, we would say the amount by which the weight needs to be changed, delta W, will be equal to alpha, which is also called the learning rate, which basically means how fast the neural network is going to adapt to the new input sets that it sees, multiplied with the partial differential of the error function with respect to that weight. Intuitively, what this equation means is the change in the weight that needs to happen in the neural network is proportional to the contribution of that weight towards the error function. We have a learning rate to ensure that the neural network does not get very used to the new input sets and still sort of remembers the old input sets that it's seen. And similarly for the biases, we have the change in the bias that needs to happen is alpha, the learning rate, multiplied with the partial differential of the error function with respect to that bias. That's it. The whole of this is backpropagation. Thus, the new weight is going to be W equal to W minus, and I'll explain in a bit why it needs to be minus and not a plus, multiplied with alpha of dou E by dou W. And the new bias will be the existing bias minus alpha multiplied with dou E by dou of bias. And here's the explanation for why it needs to be a minus and not a plus. Let me take a simple example. Let's say we don't have the bias and all we have is a single dependent called x on which the error function depends, and it's this sort of a shape, and the objective is to minimize the error of prediction, which in short means we want to adjust x such that we lie somewhere here, ideally. And to make it a bit interesting, let's say that we start off here at this point. We can clearly see that the differential at this point is negative because the slope is negative. So in order to minimize the error function, we clearly have to keep going forward, or we have to increase the amount of x in order to reach the bottom. Thus, if the differential, which is dE by dx, happens to be negative, then we need to increase x. Well, on the other hand, what happens if we're somewhere over here? We can clearly see that the differential of this function at this point is positive because the slope is positive. Thus, we understand that we have to decrease the value of x in order to reach this point here. Thus, if the differential or the slope of the error function happens to be positive, then we need to decrease x. Thus, by doing so, if the slope is negative, then we increase x. If the slope is positive, we decrease x. X will be updated. Let's say x is currently I plus 1, which is the next version of x, will depend on the x minus. So you can clearly see if this term happens to be negative, then xi plus 1 becomes greater than x of I. If this term happens to be positive, then xi plus 1 happens to be less than x of I. Going back, based on that analogy, we will update based on that analogy, we will update the weight matrix and the bias matrix by having a minus sign. For this case, we shall use the sigmoid activation function, which looks like this. If you provide x as an input to the sigmoid activation function, then the output you'll get is going to be this. This is how you define the sigmoid activation function. And the interesting thing is, irrespective of what x might be, the output will always be between 0 and 1. If x becomes minus infinity, the denominator blows up. That is, it becomes a really huge number, which makes sigmoid of x close to 0. And if x becomes plus infinity, the denominator becomes, this exponential part of the denominator becomes a really small number, thus making sigmoid of x equal to 1. I mean, almost equal to 1. And the function profile is something similar to this. It never quite touches plus 1, and it never quite touches 0, but all the values of x are squished between 0 and 1, which makes it ideal as an activation function. There's a very interesting property of this particular sigmoid function. If you differentiate z, which is sigmoid of x, with respect to x, it gives you z multiplied with 1 minus z. And we'll do the derivation of this quickly here. This whole thing multiplied with 1 plus e to the power minus x to the power minus 2, which then makes it equal to minus 1 multiplied with minus 1 of e to the power minus x multiplied with 1 plus e to the power minus x to the power minus 2. Minus 1 and minus 1 cancel each other out and they become plus 1. And thus it becomes e to the power minus x multiplied by 1 plus e to the power minus x to the power minus 2, which then becomes e to the power minus x divided by 1 plus e to the power minus x whole square. We can add and subtract 1 to the numerator, thus making it, if I bring this within parentheses, 1 plus e to the power minus x divided by 1 plus e to the power minus x squared minus 1 upon 1 plus e to the power minus x whole squared. We can cancel the numerator and the power out, thus making it 1 upon 1 plus e to the power minus x minus 1 upon 1 plus e to the power minus x whole squared. And if you remember, that's exactly what sigmoid is. Sigmoid is 1 upon 1 plus e to the power minus x. This becomes sigmoid of x minus sigmoid of x whole squared. And because we know sigmoid of x is denoted by z, it becomes z minus z squared, which in turn becomes z multiplied by 1 minus z. Thus, to sum it up, the differentiation of the sigmoid function, which is dependent on x with respect to x, basically becomes sigmoid of x multiplied with 1 minus sigmoid of x. And this will be useful later on when we're doing backpropagation. Thus, to sum it up, we've got these many equations so far. When there's an input layer, a hidden layer, and an output layer. But is this it? No, we're still missing one key point of the whole thing. This makes sense in terms of feed forward, but what about backpropagation? The next step is to derive the equations for the backpropagation. If you recall the equations, we've got two things to derive from this. One is the partial derivative of the error function with respect to the weights, and the partial derivative of the error function with respect to the biases. As it turns out, in the architecture of the neural network that we have, we've got two sets of weights. One is here, which we'll call W1. One is here, which we'll call W2. Two sets of biases. One is here, which we'll call B1, and one is here, which we shall call B2. So let's begin by deriving the partial derivative of the error function with respect to W2. We can write the partial derivative of the error function with respect to W2 as dou E by dou W2, where W2 denotes the weight that is between the hidden layer and the output layer, and E denotes the error function. If you recall, the error function is represented like this. 1 over 2n, given there's n number of nodes in the output layer, I equals to 1 to n, yi cap minus li whole squared. So using the chain rule, we can write this as dou E divided by dou y cap multiplied with dou y cap divided by dou z multiplied with dou z divided by dou omega 2. I'm just going to write a few equations on the side to make it clear what y cap, E, and z are. If you remember, y cap is equal to a sigmoid function with the z as the input to the sigmoid function, and z is equal to y dash into w2 plus b2. Alright, moving on. This can be rewritten as I'm going to take 1 over 2n as a constant here, and I'm going to call it k for simplicity. So I'm going to keep k as a constant. Dou E over dou y hat will give me 2 multiplied with y hat minus L. The second part of the equation, dou of y hat upon dou of z. This, if you remember, it's a sigmoid function, and the differentiation of a sigmoid function basically gives us sigmoid of z multiplied with 1 minus sigmoid of z. And the third part of this equation, which is dou of z over dou of omega 2, it simply gives us y dash. Y hat is sigmoid of z. This essentially, this part of the equation becomes y hat multiplied with 1 minus y hat. So, writing this equation down, finally, dou of the error function with respect to dou omega 2 becomes k, if you remember, is 1 over 2n. 1 over 2n multiplied with 2 will give us with 1 over n. So this leaves us with 1 over n multiplied with y hat minus L multiplied with y hat and 1 minus y hat, and then finally with y dash. So this I'll call equation 1.1. 1.2 will basically belong to dou of the error function divided by dou of w1. Let's now derive dou of E upon dou of W1. For the purposes of ease of understanding, let me write down the equations on the side here. Right, so these are the equations, the ones that are written on the right side that we'll be dealing with. So dou of E upon dou of W1 basically becomes dou, using the chain rule, dou of E upon dou of Y hat, as usual, as before, dou of Y hat upon dou of Z, as before, dou of Z upon dou of Y dash, as before. The two extra terms we'll have in this case is dou of Y dash upon dou of Y, and then finally with dou of Y upon dou of W1. 1 upon n multiplied with Y hat minus L. And the second term, as usual, will turn out to be Y hat multiplied with 1 minus Y hat. The third term in this case is slightly different from the previous one. If you remember, in the previous one, in the denominator we had dou of omega 2 W2. In this case we have dou of Y dash. Because we have dou of Y dash, the resultant becomes W2. Dou of Y dash upon dou of Y. Because it's a sigmoid function, and when you differentiate it, it essentially becomes dou sigmoid of Y multiplied with 1 minus sigmoid of Y. And then finally X. The equation finally becomes 1 over n. We'll preserve that the same way. I'm going to rearrange this a little bit. Multiplied with X multiplied with Y hat minus L multiplied with Y cap multiplied with 1 minus Y hat, Y cap. I'm using Y hat and Y cap as the same term in here. Multiplied with W2 multiplied with Y dash over 1 minus Y dash. So this is the final equation of dou of error function over dou of W1, which is the weight matrix between the input and the hidden layer. So I'm going to call this 1.2. Right, now that we have the partial derivatives of the error function with respect to both the weights, let's move on to finding out the partial derivatives of the error function with respect to the biases. Let's start off with dou of E upon dou of B2. This can be rewritten as dou of E upon dou of Y hat, dou of Y hat upon dou of Z, and then dou of Z upon dou of B2. I encourage you to keep a track of all of these equations while we are working with the maths, because all of these equations will be referred to time and time again. So this finally gives us 1 upon n multiplied with Y hat minus L multiplied with Y hat multiplied with 1 minus Y hat multiplied with 1. Essentially this gives us dou of the error function upon dou B2 is equal to 1 upon n multiplied with Y hat minus L multiplied with Y hat and 1 minus Y hat. And this becomes equation 2.1. 2.2 will be the same but derived with respect to B1, which is the first bias matrix between the input and the hidden layer. So let's derive that. Dou E upon dou B1 is equal to, in a very, very similar way, dou E upon dou Y cap, dou Y cap upon dou of Z, dou of Z upon Y dash, dou of y dash upon dou of y, and then finally dou of y upon dou of b1. So as we've done previously, this first term basically becomes 1 over n y hat minus L. The second term becomes y hat multiplied with 1 over y hat. The third term in this equation becomes W2. The fourth term in this equation becomes y dash multiplied with 1 minus y dash. And the fifth term in this equation is essentially 1, so we can ignore that part of the equation. So rearranging a little bit, the final equation becomes dou of E upon dou of B1, which is 1 divided by n, where n is the number of output nodes, multiplied with y hat minus L, multiplied with y hat, multiplied with 1 minus y hat, multiplied with W2, and then finally multiplied with y dash and 1 minus y dash. And this whole equation becomes 2.2. And that's it. Those are all the equations that you actually need in order to build a neural network from scratch. The equations 1.1, 1.2, 2.1 and 2.2, they all pertain to backpropagation algorithm, and the rest of the equation basically deal with the feed-forward part of the neural network. Now, in order to recap all of the equations, I'm going to write them out here one by one. Right, so the first equation that we got was y is equal to x multiplied with w1 plus b1. Y dash is, after we perform a sigmoid function over y, z is equal to y dash multiplied with w2 plus b2, and then finally y hat is equal to a sigmoid function over z. The differentiation of a sigmoid function with respect to z yields the same sigmoid function multiplied with 1 minus the value of the same sigmoid function again. So these 5 are the essential equations in order to perform feed-forward part of the neural network. And the change that happens in the neural network is the delta of the weights is equal to whatever weight was previously minus alpha, which is the learning rate, and dou E upon dou of that weight. Similarly, the delta bias is equal to the previous bias minus alpha of dou E upon dou of the bias. And moving on to the backpropagation part of the equation, dou E upon dou W2 is equal to 1 upon n multiplied with the y dash and y hat minus L multiplied with y hat and 1 minus y hat. Similarly, dou E upon dou W1 is equal to 1 upon n multiplied with x, then y hat minus L multiplied with y hat upon 1 minus y hat multiplied W2, and finally with y dash multiplied by 1 minus y dash. And the same for the biases. And the same for biases is going to be dou E upon dou B2 is equal to 1 upon n multiplied by y hat minus L multiplied with y hat and 1 minus y hat. And similarly, dou E upon dou B1 is equal to 1 upon n multiplied with y hat minus L, y hat, 1 minus y hat, W2. And then finally y dash into 1 minus y dash. These are the only equations we actually need in order to make our neural network from scratch. And this is not a general equation, but it's a very specific equation for our neural network, which so happens to have 2 layers. And by 2 layers, I mean there's an input layer, there's a hidden layer, and there's an output layer. And it's important for me to mention that the connections between the input and the hidden layer are W1 and B1, where W1 is the weight and B1 is the bias. And similarly, the connection between the hidden layer and the output layer is described by W2 and B2, where W2 is the weight matrix and B2 is the bias matrix. Alright, so that concludes all the mathematical derivations that we need in order to make this neural network to work. There's a few considerations that we need to take care of, but I'll explain the things that we need to take care of. For example, how do we initialize the W1 and B1? Should we initialize by 0, or can it be a random initialization? If it's a random initialization, can it be a random uniform, or does it have to be a random normal initialization? So this and many more considerations, which are more pertaining to the programming consideration, will be taken care of in the next video, when we implement all of these mathematical equations purely in Python using just a NumPy library without using or touching any machine learning or neural networks library. So I hope you guys are all excited to build your own neural networks from scratch in Python and in NumPy. See you in the next video. Thank you.